So we'll go on to our next talk, which is by Freeman and on the safety management of autonomous robotic systems, a test of resiliency.
First of all, I'm glad that to share my outlook on the management of a relatively new technology, swarm robotics. And in the beginning of this talk, I would like to talk a little bit more about what is swarm robotics, and then I will go on to the topic, the safety management of autonomous robotic systems and a test of resiliency, because this is important because eventually we will want to develop standards as well as be able to certify these swarm robotic systems. Next slide, please. Next slide.
There you go.
Okay, swarm robotics are more than just networks of individual independent agents. They're potentially reconfigurable in communications, capable of coordinated sensing and interaction with the environment. The knowledge of the swarm is distributed amongst all the robots, where one is not able to accomplish the task without the others in the swarm. So the basic principle of operation is simple programming knowledge that helps to coordinate a common goal executed by a group of robots. Next slide, please. The first robotic swarm is scheduled for delivery on the moon in 2024. NASA's commercial Lunar payload services will deliver a Nova C lander along with 4 Cadre rovers to a lunar region called Reiner Gamma in a mission to learn what lunar swirls are, how they are formed, and their relationship to the moon's magnetic field. That's sparsely. Cadre, or the Cooperative Autonomous Distributed Robotic Exploration, consists of 4 mobile robots programmed to work as an autonomous swarm to explore the lunar surface, collect data, map different areas of the moon in 3D. Next slide, please. Swarm behavior can be likened to that of insects. They are beautifully engineered examples of kind of software in use. These insects do not use centralized communication. There's no strict hierarchy and no one in charge. For example, ants use the approach to find the most excellent route to food source. And individual ants do nothing more than follow the strongest pheromones trail left by other ants. But by repeated processes of trial and error, the best route to the food is quickly revealed. Similarly, local interactions between nearby robots are being used to produce large-scale group behaviors from the entire swarm. One of the main aspects in robotic swarms is that the control is decentralized and distributed among the robots. This characteristic allows the emergence of collective behaviors from the robots' interaction with each other and with the environment through their embodied sensors and actuators. So the need for behavior scripting and archiving of such scenarios suggests that we will incorporate artificial intelligence and machine learning in the robotic swarms. Next slide, please. Compared to more conventional systems engineering processes, autonomous control systems demand more upfront analysis. Its main benefit is increased reliability due to fewer errors of omission, fewer errors of translation into software, and more easily understood operational controls. At the bottom of this figure, the functional layer consists of a control software for the robot's hardware. Then the intermediate layer utilizes a middleware framework, which is an open source robotic operating systems that provides an interface to the hardware components. The upper layer contains the decision-making components of the robotic system, which captures its autonomous behavior. Next slide, please. There is a clear distinction between the control system and the system under control because control can only be understood and exercised intelligently through models. Next slide, please. Next. Modeling a system under control assures consensus among the systems engineers who start with a design of the hardware system so that standard operating procedures are performed in accordance with the requirements for the system's mission. System behavior produced of operations is reviewed for control mechanisms by multiple systems engineers. However, software engineers translate and code these standard operating procedures and requirements based on the understanding of the multiple systems engineers' consensus. Therefore, software engineers are tasked with a software design appearing not as rigorous as the hardware design. Multiple sensors and communications deployed in a physical environment activate sensor inputs for autonomous decision-making components. So modeling a system under control becomes really a system behavior plan that, number one, informs system design, and two, minimizes systems engineers' translation errors in defining and understanding standard operating requirements and procedures. Next slide, please. While decisions and actions might normally be taken by a competent human inspector, now the decisions and actions need delegating to a robotic inspector. In most non-trivial environments, the answers to such questions cannot all be encoded beforehand. And so the autonomous system must make the most appropriate decision given the information that it has at that particular time. So with validation and verification, you'll be using decisional bounds or a set of prescribed decisions. Formally, you need to verify that the system always works within these restrictions. Two, you have to test a range of scenarios to ensure that the system always works within these restrictions. And this might be a real physical testing or testing and simulation. And three, use runtime verification to monitor whether the system follows these restrictions in practice. So, per fully autonomous decision making, you need to formally verify that the system makes the right decisions. There are some issues with this, and some of the issues include are the correct decisions being made given the information available? So, you have to verify this. Is the decision making transparent, both for explainability and verifiability? How effective and reliable are the self-awareness, that is, with the sensor and the control actuator, and the fault recognition capabilities? And what happens or what guarantees this verification that we can provide for this particular aspect? Next slide, please. So we have four levels representing the different aspects of robots. The first aspect, let me move on. We're losing time. So I'm going to skip to some of the safety right now. So let's move to the next slide. Okay, in this slide, we want to start talking about resiliency. Resiliency and robustness are two very important metrics that we need to talk about. But when we talk about resiliency, this is how fast and how fully recoverable can a system recover if it becomes vulnerable and it becomes non-functional. And so we really start off with the reliability metrics. And I gave you an example here with the Apollo era. Now, with the resiliency analysis, we're basically looking at the safety integrity levels. And so with the next slide, please. Next slide. And so you here in this particular chart, the one before that. And in this particular chart, you can see that there are several stages where there is a vulnerability stage, and then there's a recoverability. How we have this recoverability is that we look at the system's component information measures. This becomes part of the reliability analysis. And with these kinds of measures, you're able to find out how much of each component is really impacting the non-functionality of the impact in the non-functionality of the system or the swarm system, and therefore you want to be able to target some of these components in a certain kind of ranking such that we can have a near full recovery. Let's go to the very last, the next to the last slide. Okay. So In conclusion, robotics for lunar surface operation was first studied in 1989, updated in 2019 to include reusable, modular, and interoperable framework for space qualifiable space autonomous robotic software systems. There is a clear distinction in autonomous robotic systems between the meanings of control system and the system under control, which explicitly represents the behavior models. Next, system operational behavior is controlled through software design, best optimized when software engineers translate and code system engineers' understanding of the operational behavior. Next, the certification processes often require safety cases showing structured argument of system safety in a certain context. And lastly, optimal behavior of autonomous robotic systems is evidenced by two qualitative measurements characteristics, robustness and resiliency, when quantitatively measured, help to standardize and lead to certification of the autonomous robotic systems. And I want to thank you. I'm sorry, I didn't have much time left. Thank you.